Welcome to the Crazy Hat Chemist. So another video here on thermochemistry. So let's get moving. Bam! So today we are talking about a generic heating curve. It's a temperature versus heat graphic. So you notice that the temperature is along the y-axis. The heat, the constant heat, is along the x-axis. And I've drawn an idealized graph right here where you should see that it's not nice and smooth. There are certain points here that are absolutely straight and absolutely flat. They have sloped sections and flat sections. It's idealized, but most graphics will look this way. Okay, this here denotes the melting point. So this first flat section of the graph is the melting point. The second flat section of the graph is the boiling point. These two temperatures define the graph. So you need to know for your element or your compound what the melting point and boiling point are, and they will define the graph. That's very important that you delineate those on the graph. Okay? Then the other part about this graph that you need to know is that the three sloped sections, the lowest one, making sense, would be a solid at the lowest temperature. Then one slope section up from that would be a liquid. Then the next slope section up from that would be the gaseous state. So you have our three states of matter: solid, liquid, and gas. Now, in between the solid and the liquid is the conversion between the solid and the liquid. In between the liquid and the gas is the interconversion between the liquid and the gas. Okay? Now, on this graph, you can go from a low temperature all the way up to a high temperature. Or alternatively, you can go from a high temperature and then work yourself down to a low temperature. Both processes will work perfectly fine. That is, you're adding constant heat or you're cooling it down constantly, one or the other. All right, now the next part here is that we need to know the math that we're going to be using for each one of the steps along this graph. So this first step here, where you have a solid, is you're going to be doing Q equals MC, the specific heat capacity for ice, times the delta T, which is the change in temperature. Okay? The next sloped section, the next state of matter, which is a liquid, is Q is equal to MC for the liquid times the delta T. And then the gaseous state is Q is equal to MC for the gaseous state times the delta T. Notice that there's something very similar, and there's one thing that's very different for all these three states of matter. They are all Q equals MCAT. That is for certain, and that is the constant that is occurring here. They all use the same mass. They all use the different change in temperature depending on where you are on the graph, but the equation is the same, and that is the delta T is being used in all three cases. Where it differs is that the constant that is used is specific for the state of matter. If you are not given a constant, you will have to either look it up, or you might be given a constant for just the liquid state and use that for all three. It's a good approximation, doesn't work every single time. Now, we got two flat sections of this graph, and we need to get the math associated with that. Now, this is the first flat section, which is the interconversion between a solid and a liquid, or a liquid and a solid. And that is the Q is equal to MC for the heat of fusion. Okay? Now, notice on this, there's no delta T. There's no temperature change. Why is that? Because this is a flat section. And if you look at that on the y-axis, there is actually no temperature change because it's horizontal. So there's no temperature change. That's a zero temperature change, but you're not multiplying by zero. Okay, that is the heat of fusion, that constant which you're using. Now, the next flat section of this graph corresponds to the boiling point. Okay, and that is the Q is equal to MC. The C is the heat capacity for the heat of vaporization. Now, also at this flat section, there is no delta T, there's no change in temperature, but there is interconversion between the liquid and the gas state, or the gas and the liquid state at this point in time. Okay, so here's a way to remember these. Okay, if you're really good at sports, you get into the Hall of Fame. That is the heat of fusion, the Hall of Fame. Now, if you're like way beyond that, then you get into the next hall, and that top hall, instead of the hall of Hall of Fame is the Hall of Victory, and that is the heat of vaporization. So hopefully you got that. Okay, I'm going to label these as step 1, step number 2, step number 3, step number 4, and step number 5. These 5 steps have specific math that's associated with them, specific temperature changes or no temperature change, and then a specific constant that is used. At each of these 5 steps, a different constant is used. So what is the constant that is used at each of these steps? Now you should be able to find these in your textbook, or if you look in the CRC, that is the Handbook of Chemistry and Physics, you will find it there. So here they are, and these are the constants for each of the 5 steps for water. I'm going to start off on the bottom at step number 1 because that's the way the graphic works. And step number 1, it says the specific heat capacity of ice. The CP of ice is 37.8 joules per mole Kelvin. Step number 2, the heat of fusion for H2O is 6.01 kilojoules per mole. Okay, again, notice that there's no temperature. Step number 3, specific heat capacity for water, CP for water is 4.184 joules per gram Kelvin. Notice that we've been using this number all this time, except we've been using 4.184 joules per gram degrees Celsius. But I'm hoping that you know that the change in temperature, whether you're using Kelvin or degrees Celsius, actually doesn't matter. So you could replace the kelvins in each one of these constants with degrees Celsius, and it'll be perfectly fine, because the change in temperature for degrees Celsius and degrees Kelvin is the same, because the interval for Kelvin and degrees Celsius is the same. Now let's go to step number 4. The heat of vaporization is 40.7 kilojoules per mole. Again, no temperature, because this is a flat section of the graph. And then the very last one, step number 5, the specific heat capacity of steam. The CP of steam is 36.5 joules per mole Kelvin. Those are the constants for water. Now, if you have a different compound or a different element, you're going to have to look up the values for those specific constants along that entire graphic. But many times, chemistry teachers use this as an example. They use water and then move on to other compounds or substances. Okay, I am the Crazy Hat Chemist, and of course, I've got a great crazy hat here. Okay, this is, I'm all in favor of world peace. Okay, but I'm also in favor of world peas as well. Give me a thumbs up if you like that video. Give me a thumbs up if you liked world peas or world peace. Subscribe to my YouTube channel, and I'm going to see you next time for more cool chemistry videos. Check out the website. Bye for now.